Very good. You're sticking with it. We're going on and talking about acids and bases. So, acids and bases, they are very important for our society. And so, here's some really common acids. So, hydrochloric acid, that's the acids in our stomach, also known as muriatic acid. So, we use it for various things like cleaning metals, also in swimming pools. Sulfuric acid, also known as battery acid. Of this, what we do this quite a bit for is in fertilizers. So, what we make of the largest chemicals, anything, is fuel. The second largest thing that we make in terms of chemicals are fertilizers. So, fertilizers are very important because we've industrialized our agriculture. So, what does that mean for society? Well, if you look before the Industrial Revolution, we had about half of the population geared towards food production. So, if you look back before that, before we've industrialized things, specifically our agriculture, most of the half of the population was geared towards food production. Now it's about 5%. So because of that, we have a very few people are involved in food production, and also we've got lots of food, and that's one of the reasons why we have a huge population boom. We went from the year 1900 of 2 billion to 8 ish billion right now. So how could we have doubled twice in the past 100 years? It's because of food production. The other thing is likely from antibiotics. Okay, so nitric acid as well, fertilizer. Acetic acid, that's in vinegar. So it's common acid in vinegar used for various things like in plastic and rubber. Citric acid used in food. So carbonic acid, we use this to drink. Hydrofluoric acid, this stuff is scary. Okay, hydrofluoric acid. This, if you get it on your skin, it's a surface anesthetic, so you can't feel it. So and it's bone seeking, so it'll start to dissolve your bones, and you really can't feel it. So it's pretty scary. Don't use it unless you have to. But they use it to etch metal, and also for glass. So if you've ever seen like frosty glass, that's from hydrofluoric acid. So hydrofluoric acid eats glass. Sort of thing. Phosphoric acid used as a fertilizer, also in food. So you can put it in some drinks. So here's some common bases. And notice here sodium hydroxide, potassium hydroxide. Sodium hydroxide sometimes is called lye, 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 sometimes called caustic. Um, so used in petroleum, making soap. Potassium hydroxide, so various things, batteries have potassium, alkali batteries tend to have potassium hydroxide in there. Sodium bicarbonate, that's baking soda. Sodium carbonate, that's known as washing soda. Use it for glass, and just use it to clean a lot of things. What I use for my dishwasher, I use sodium carbonate. It's also a primary component in OxyClean. It's also known as washing soda. Ammonia, mostly used to make fertilizer. So for ammonia is the main source of nitrogen that we have for plant nutrients. So acids and bases are important for industry, specifically fertilizers. So very specifically fertilizers. So let's talk about acids and bases. This is a definition. So we have the Arrhenius law of acid-base. Acid forms hydrogen ion or hydronium ion in water. Base forms hydroxide in water. And I'm going to use hydrogen ion and hydronium ion interchangeably. The textbook uses hydronium ion, H3O plus. But then the textbook, when we get to electrochemistry, it switches back to hydrogen ion. I'll probably stick to hydrogen ion just because it's easier to write. Computer models suggest that it's H3O plus and not H plus, but the truth in that is we really don't know. One of the things is this is something that we may not be able to test because when we do spectroscopy, look for things, we look for electrons, and a free hydrogen ion has no electrons, so we really can't track it by using normal types of spectroscopy. There's other types of spectroscopy that we can use, but is the hydrogen is the proton going to be what differences are the energy levels and magnetic properties of a proton? Are they free versus bound? It's not really we at least don't have the resolution to do anything right now. Maybe in the future, but right now we really don't know. And computer models suggest H3O plus, so the textbook tends to go with that. But that's not real knowledge, though. At least not in contemporary science. But okay, well, Bronsted-Lowry. This is kind of where we're going to stick with this book, uh, where acid is a proton donor, base is a proton acceptor. The best definition of acids and bases is Lewis acid is an electron acceptor and base is electron donor. And all of these are equivalent, well, Lewis acid and base being the best one. So the idea here is I've drawn here with the water. One of the ways you can break bonds, if you remember from last semester, you can break bonds by adding electron density to the antibonding orbital. So we have the water molecule, and you add electron density to the antibonding orbital, it'll break that bond. So that's how the protons moving around can be viewed as a transfer of electrons. So it's whatever way you want to model it, but it's the electrons are the ones that are going to move around. And something for this equation here. So let's talk about some of the definitions. And Bronsted-Lowry. So Bronsted-Lowry, we're going to focus on is that acid is a proton donor, base is a proton acceptor. So look here, we have ammonia, the base, and it becomes ammonium. So that's the base being a proton acceptor. It goes from NH3 to NH4. So that extra hydrogen, it's accept another hydrogen. So water, it goes from H2O to H1O or OH, right? So it's lost a hydrogen, so it's a proton donor. That makes it an acid. But in equilibrium expression, so we can go both ways. So the base in one direction is a base, but in the reverse direction, now NH4 to NH3, it loses a proton. That makes NH4 a acid. And it's an acid, and it's on the other side of the equation, so it's a conjugate acid. Same thing with hydroxide, it's a conjugate base. It's a proton acceptor, but it's just going the other way. So, and here's another thing with water. Hydrochloric acid plus water makes chloride and hydronium. So you have one case water acts like an acid, one case water acts like a base. That means that water is amphoteric. It is both an acid and a base. So that's another interesting thing about water. It's not necessarily unique. Amino acids are also amphoteric. But water, as I said before, is a very strange compound. So we have to identify these as acids and bases, and conjugate acids, conjugate bases. So if you are not colorblind, note that I've written acid in red and base in blue. And you'll see very commonly acids written in red and bases in blue. So one of the properties of acid is there's a indicator called litmus. Acids turn litmus red and bases turn litmus blue. And because of that, we oftentimes refer to acids being red and bases being blue because of that indicator. Other things about acids and bases: acids taste sour to humans, bases taste bitter. And when I say bitter, I mean like cheap medicine bitter. Like if you get an off-brand generic type of medicine and it's like cough syrup. You eat cough syrup, you take it, like, what is this stuff? And it tastes bitter. That's what the bitter flavor is. Most foods are acidic, so you won't taste anything bitter really in food. Caffeine is basic. You can taste bitter in that, but well, with that, humans tend to not like bitter things because bitter things are poisonous. Caffeine is really poisonous. But if you look, like a cup of coffee is 100 milligrams of caffeine. 100 milligrams, that's not very much, right? I mean, if you took grams of caffeine, you can die from that. So the dose of caffeine is always going to be very, very small. In the order of we can measure it in milligrams. So, anyways, how do we solve this one? So remember Bronsted-Lowry. Acid is a proton donor, base is a proton acceptor. So first one, H2SO4 goes to H1SO4, loses a hydrogen, it's an acid. Water goes from H2O to H3O, it's a base, it's a proton acceptor. And that means the other direction, although this is a strong acid, it only tends to go one direction, but I'm going to go ahead and say the bisulfate ion here, HSO4 minus, that is a conjugate base. and the hydronium ion is the conjugate acid. Same thing with bicarbonate here, HCO minus, and water. That the bicarbonate goes to carbonic acid. That means it's a proton acceptor, it's a base, and H2O water is it's going from H2 to H1, so it's an acid. And then in the reverse direction, carbonic acid is the conjugate acid, hydroxide is a conjugate base. So this is for you to try. Which one's a conjugate base? It's the proton acceptor. It's the bicarbonate. And notice it's always on the conjugates are always on the right side, on the product side. So let's talk about strong acids and weak acids. Strong acids, these, as I write this, HCl in red, strong arrow over to H plus Cl minus, is not in equilibrium. There is no equilibrium. It breaks apart. It's a strong electrolyte. So if you remember from last semester, a strong electrolyte is something that breaks apart completely in water, and that's what hydrogen chloride does, hydrochloric acid. So it is a one direction. And the strong acids, they are hydrochloric, hydrobromic, hydroiodic, nitric, perchloric, and the first proton on sulfuric. So the easiest thing to do is just memorize these. I usually don't tell people to memorize things, but just if you memorize those, and everything else is a weak acid. So if you do that, then it'll make your life much easier. So weak acids, and so strong acids are strong electrolytes, they break apart easily. Weak acids tend to stay more molecular, and they have equilibriums associated with them. So they prefer to stay together. So like a weak acid is like a really clingy couple. You see them together most of the time. Do they spend some time apart? Sure. When one's going to the bathroom or something like that, they are not together, but pretty much they always see them right next to each other hanging out. That is a weak acid. And weak acids the same way. They prefer to stay molecular. Occasionally they will ionize, and they were also known as weak electrolytes. So that weak acid there, I just said HA is the generic acid plus water makes hydronium and conjugate base anion. So the Ka is the hydronium times the anion over the acid concentration. And I'll tend to use the bottom one that says easier. I tend to go with the HA equilibrium with H plus over A minus. So, okay, and if you memorize this, remember all other acids are weak, and some common weak acids, so hydrofluoric, already mentioned. So remember, hydrofluoric is not a strong acid. It is not a strong acid because it forms a hydrogen bond network with itself. It tends to dimerize, so it forms two, and then a dimer it becomes a weak acid that way. So then sulfurous acid, so that's just one less oxygen from sulfuric. Carbonic, already mentioned that before. Acetic, already mentioned. Phosphoric, formic acid. This is what's in ant bites. So it's the venom that's in ant bites. A formis from the Latin word for ant. Okay, so now water also autoionizes, meaning it will disassociate itself. So water will break apart into hydrogen ion and hydroxide, or hydronium ion and hydroxide ion, however you want to say it. So that is the autoionization of water. And water has the equilibrium constant. So now we're applying equilibrium constants. So the equilibrium constant for the dissociation of water is 10 to the minus 14 at 25 degrees Celsius. And now you probably are familiar with the term pH. pH is the minus log of the hydrogen ion or hydronium ion concentration. Likewise, the pOH is the minus log of the hydroxide ion concentration. It's a logarithmic scale, meaning every one step unit is a factor of 10. A couple other things, the pH plus the pOH is 14, and that works for 25 degrees Celsius. And when it comes to sig figs, they are always after the decimal point. So when you do sig figs in calculation, they are after the decimal point in dealing with pH or pOH or P anything, really. And a way to go from pH to back to hydrogen ion, you take 10 to the minus pH. So here's some common things with the pH of some substances. So pH of 7 is considered neutral, less than 7 is acidic, greater than 7 is basic, also known as alkaline. So here we go, and then so here's some things. So stomach acid is pH of 1 to 3. This is when your stomach is actively digesting, though. If you haven't just eaten, your pH is probably about 5. But okay, and limes, you can see limes are very acidic, as are lemons, not surprising, and various food. Food is pretty much all acidic. And human blood, we are slightly alkaline, mostly neutral though, and various and other things. Egg whites, slightly alkaline. There's not very many foods that are, in fact, alkaline. And then there's some other things. So caustic solution there, 4%, pH of 14, very, very basic, very alkaline. And here's showing the pH scale. It's just showing that pH is 10 to the minus pH. Or 10, I'm sorry, hydrogen ion is 10 to the minus, I'm sorry, pH is equal to minus log of hydrogen ion concentration, and vice versa. Hydrogen ion is 10 to the minus pH. So a solution goes from pH 6 to pH 3. How much does the concentration change? Don't forget that pH is a logarithmic scale factor of 10. This is 1,000. Okay, so let's do some more calculations. Calculate the pH of these solutions and say if it's acidic or basic. So for part A, it's so pH is just minus log of the hydrogen ion concentration, 1.8 times 10 to the minus 4. So this is just straight shot. This is 3.74. And so remember, 2 sig figs after the decimal point, this is acidic. So, and then the next one for B, there are 2 ways to solve it. I'll show you both. So, so the pH is minus log of the hydrogen ion concentration, and so but Kw is 10 to the minus 14 is equal to the hydrogen ion times the hydroxide ion. And if you're given the hydroxide ion, so that means that the hydrogen ion concentration is equal to 10 to the minus 14 divided by the hydroxide ion concentration, which is 10 to the minus 14 over 1.3 times 10 to the minus 2. And then we have minus log of 10 to the minus 14 over 1.3 times 10 to the minus 2. Putting that in your calculator, you get 12.11, or a base. And the other way you can do it, if you want to do this other way, the pH plus the POH equals 14. So that means the pH is equal to 14 minus the POH equals 14 minus the minus log of 1.3 times 10 to the minus 2. You put that in your calculator, and then you'll also get 12.11. So it's whatever method you prefer. I'd probably do the second method myself. But okay, then what about the other way around? How can you calculate hydronium ion concentration from pH? So the hydrogen ion is the same thing. It's just 10 to the minus pH, 10 to the minus 4.8, and you put that in your calculator, and you get equal to 1.6 times 10 to the minus 5 molar for that. Okay. And moving on. So here's POH. pH and POH, you can see that they are kind of in vice versa of each other, at least as far as 14. And later on, we'll talk about the pKa. That's just minus log of the Ka. So the P just means minus log of things. All right, let's go and talk about some more equilibrium stuff. So we just covered equilibrium last chapter. Let's do this again. So what is the pH of, or what's the hydrogen ion concentration of a 0.1 molar hydrogen cyanide solution? So hydrogen cyanide is a weak acid, And the way you do this, you start with 0.1 here and 0, 0. So nothing there. So remember that with equilibrium, so start with reactants, no products. What are you going to do? You're going to shift right. So plus x here. So lose 1 extended reaction of HCN, gain 1 extended reaction of hydrogen and cyanide. And so this is 0.1 minus x, x, and x. Our Ka is products over reactants, which is 4.9 times 10 to the minus 10 equals, so x squared all over 0.1 minus x. And this is when you can apply the x is small, x squared over 0.1. So you have 4.9 times 10 to the minus 11. So equals x squared, and this is equal to 49 times 10 to the minus 10. So x equals 7 times 10 to the minus 5. So you can use your calculator there if you want. So wait a second. No, minus 12. This will be minus 6 then. Sorry. 7 times 10 to the minus 6. So and yeah. So yeah. This one you don't really need a calculator, but you can use your calculator if you want. And it just wants a hydrogen ion. X is equal to hydrogen ion, so you can just set that to the hydrogen ion and you're done. All right, so why don't you try this one out for nitrous acid using the x is small approximation. See if you can get that there. And we are done for this chapter, or not chapter, with this section. So more is coming.